Hi, I'm Sander. I'm a finishing graduate student from Ghent University, and I'll talk to you today about how to develop, let's say, scientifically oriented Python package built with Parsl. So the domain of application is also molecular simulation. So roughly speaking, the workflow of molecular simulation tools looks like this. You have some notion of the atomic structure. You have some notion of the interaction energy between atoms. That's usually something that quantum mechanics or DFT, for example, can give you. Then you need to run dynamic simulations, which analyze how the particles move. And then from that, you can compute physical properties. Now, if you look at the resource requirements of typical workflows in molecular simulation, then it would look something like this. So it's quite heterogeneous and quite unbalanced. You might have to do a lot of DFT calculations, which require a lot of CPU. Then you need maybe to train your model, which requires one GPU, some aggregation, and then large dynamic simulations, which again require a lot of GPUs. In addition, it can get a little more finicky because sometimes dynamic simulations are coupled to each other, and then you want a large number of GPUs at the same time. So basically a multi-node allocation. Or you may need to do some high-level quantum mechanics, and in that case, you need specialized nodes with large amounts of RAM, which are not, or which are typically available in separate Slurm partitions, for example. So it's quite a bit of a mess. And so if we look at the number of tasks or elementary number of operations that are being done, of course, like the load is focused around or scales with the blocks. But in terms of like individual tasks in Parsl language, actually, the big consumer is like the pre and post processing. That's where you spend most of the tasks. They're very short, but you still have to take these into account. So if you develop for, if you develop a framework like this, then there's a few things to keep in mind in terms of the tasks. As I've said, many of these tasks are quite computationally expensive, and the duration is non-trivial, as in it takes hours to days, and this becomes on the order of the wall time. In addition, users want to see output of these tasks. There is absolutely no way you're going to convince anyone to use a software package that will hide output from it. This requirement alone is already quite stringent. Second part is you need a way to deal with large numbers of tasks that are very, very small. Then in terms of the resources, so heterogeneous, as I've said, and sometimes multi-node. And then finally, we're developing for scientists. And then scientists, they don't always, not always very proficient in programming, and they are intellectually capable for sure, but they do not have the time to, look into this very deeply. So you really need to make sure it just works for them. And then also, with these integrated workflows, the dependencies also get more tricky. If you look at quantum chemistry software on HPCs, it's typically installed in modules, and these modules come with Python itself. But then there's also PyTorch that you might have to install, and Parsl is kind of finicky with Python versions, sorry, so it can become a bit of a mess. So, okay, how do we get users to use Parsl if they don't know Parsl? So the philosophy is basically you only allow them the freedom to choose a provider, and basically everything else is more or less fixed. That they can also reasonably understand because, well, okay, you have to run calculations, so you have to determine like the Slurm account number and stuff like that. So that's pretty straightforward. And so in the workflows that I talked about, there are basically three main things. There's you use your ML model, you train your ML model, or you generate data for your ML model. And literally everything falls into these categories. Well, they have to specify Slurm for each of these categories. There are a few additional options that users have to give, such as cores per worker, which we know from the executor class. Most notably, they're not allowed to actually specify executors or launchers because really, in any given situation, there's usually one sensible choice, and that choice is forced on the user such that they don't need to know what an executor is and what the differences are. Right, so these are hard-coded. To resolve the dependencies, we chose to adopt a containerized approach. Basically, all of the heavy lifting, all of the operations which require dependencies are executed in Aptainer container engines. So if they don't know what Parsl is, but you just give them the option to specify slurp parameters, that's still fine. But one way or another, if you're building an asynchronous workflow, you're gonna have to realize that it's asynchronous, meaning at some point in that workflow, you're gonna have to deal with a future. The approach we take here in psiflow is that we wrap most of the futures such that they're basically hidden from the user. What I mean by that is, so this is a brief overview of what the API looks like. None of these objects are futures, but a few of these actually define internally tasks that are then executed. And then, if they generate a new file, then they generate a new data future, but the user himself or herself doesn't really see this. The thing is, of course, at the end, there is, at some point you can't escape the fact that whatever result you're computing, whether it's an error metric or a physical property, it's going to be a future. We restrict it to be simple features, as in Python primitives or NumPy arrays, but that's it. Right, I think that's the end of it. So this is the repository. If people are interested in how we built this, then feel free to take a look or ask me questions.